Right. For those of you in class, I handed some homework back. I'll work on the online stuff this weekend. I don't have the scores in Moodle yet. I'll put them all in at once when I grade the online stuff. Um, Now, one thing I did notice, I just kind of graded a lot on process on this one. A couple of things. One is I'm asking you for the answers on the bottom usually, and then I would like arrows showing the direction that the forces act. So remember to do that. There were people who weren't doing that. Um, okay, another thing too is I was catching some errors in the setups as best I could. If you're, I do get the impression, very frankly, that there are some folks who are setting stuff up perhaps incorrectly and then somehow getting the right answers, which might be due to the fact I give you the answers, I'm not sure. But I would advise against that. If you're coming up against something and you're setting something up and something's not right, and if you can't figure it out, just put a note in there, say, I don't understand what's going on, and I'll answer it. When you get the right answers from a wrong setup, I don't notice that. And then you might be learning something incorrectly if you're doing that. So I would encourage you to not focus so much on the points you get out of the homework as much as learning from it. So if there's something on there you don't understand and you can't figure it out, put a note on there, and when I grade it, I'll answer it, okay? I would not suggest setting it up incorrectly then putting the proper answers down in the answer blanks. I don't think that's a good way to learn the material. So I just mentioned that because I was noticing that a few times. And I can't, when I see the right answers there, sometimes I'll miss the errors in the setup because I can't, it's a lot of detail to scan through with all the signs and things. So be aware of that. All right, so we've got a few of these that are due on Monday. So are there any questions I want to turn back? All right. Okay. So we got 3 of them that are due. The first one is this cart on an incline. Are we okay with this one? Do we have questions? So what's the basic idea on this one that I'd like to get across to you, suppose? How would you approach this one? Yeah, I think so. Yeah, of course, first thing you do is you draw a free body diagram. We're going to have the weight here, right? Like so, you are given the weight, so you can put that on there, 2,300 newtons. You do have reactions. Those are rollers, basically, is what they are. That's what wheels are. So you'd have, so we got RA, RB. We do have a frictional force that's keeping this thing from rolling. So a moment where 2 of those forces intersect, I think that might be a good spot. What's the other little bit on this one? What might be the way to approach that? Any little extra thing we might want to do?
You might want to redefine your coordinate axes along the x and y plane.
Yeah.
And then change your cosine to affect the gravity.
Yeah, I think that would be the way to do it, because you notice that 3 of the 4 unknowns are all aligned on this axis system. So I would definitely approach it like this. It'll be a simpler problem if you do. And then the one angle you need now is this one here. Now that's going to be the same as the ramp angle. That's going to be 26 degrees. Because what's going on there is we've got a 26-degree ramp. And then we're kind of using an axis normal to that. And then we have a vertical force like so. So, it's a little bit of a geometry problem there. I guess if we went like this and extended that down, this would be 90 minus 26, wouldn't it? Otherwise known as 64. So that's 64. And then if I extend this down to the right angle there, I'll take 90 minus 64 and get back to the 26. Okay. So that's how you could figure out that angle. So by putting that angle up there, I think, and using an inclined axis system, that becomes a much more straightforward problem, I think. So I would definitely approach it in that way. Now, when we do that, we want to start with a moment about the point where 2 unknowns intersect. So I think A is a very good point. Now, it's not the central axis of A, it's the base of the wheel, because the friction acts there too. And set that equal to 0. And then now when you do that, I think what's going to happen next is you're going to have this force at the center of gravity. So you're going to, as you might see that, you want the adjacent component, so that'll be cosine 26 times the 2300 newtons. And then the moment arm on that will be the 0.6 meters. And that will come around clockwise, I think, so we want a negative sign on that. Okay. Now, there's another component that involves the 2300, and this is one that people, from my experience, are apt to forget. So put another component there. I think you see you're going to have a component parallel to the ramp, and sometimes people will forget that. So remember to include that, okay? Up there in the moment equation. And then you'll have an additional term with RB. And of course, you want a moment arm on that. So something like that, I think, would be the way to go.
What about the friction force? Wouldn't that be?
It's acting right through the point where we're taking moments about, so we don't need to include it in the moment equation because we're taking a moment about the base of the wheel purposely to get that out of there because we don't want to deal with it. Okay. All right.
So you get RB out of it.
Yeah, so you can get RB out of this equation. So are we all right with that? And y'all with me on that second component there?
So is the moment about A going to be equal to friction F?
No, the moment is a moment, and the moment about A will be 0 because it's in static equilibrium.
Yeah.
So, they're kind of different things, forces and moment. I'd do some of Fx prime to get the friction, which will involve that component of the weight acting parallel to the ramp.
Okay.
And are there any questions on that second component there that I've just shown with the 2300 on this one here? We good with that? That's something sometimes people focus on, the one that's perpendicular to the ramp, but they forget the one that's parallel to it. So I just want to mention that to you, so that you're sure to get that one up. All right, so we good with that?
That green arrow is the cosine rotation, right?
That green arrow is, let's see, and this sketch is rather small. So what we got here, we got a car, like so, and then we've got the center of gravity of the car, and we have the weight that is X down. So what we want out of that is the component like that, and then we also want the component that I drew in green like that. So that's what that green component is. And I don't know if it's cosine. I think it depends on the angle you use, of course. All right, so we want to break that weight into two components on the X prime and Y prime axes. So are we good with that one?
Yep.
Questions on that? Okay. All right. Okay, so that's that one. Now this one here, this is a dam, and I mentioned this before. This is a way I've modeled a little dam before. When you build a dam, you have these, the water pressure builds up, and it starts pushing the water around, around your dam, under your dam, wherever it can go. So you put what's called a cutoff wall under the wall that breaks the water. You also have a cutoff wall that extends down into the soil. How deep that goes kind of depends on how high your dam is and how permeable the soil is. But that extends down. It serves two purposes. It prevents the water from kind of sneaking under the dam, kind of doing that, which it will try and do, which is bad. And then it also anchors the dam so the water just doesn't push the dam down the river. You can model that like a pin joint. Now, obviously, it's not a pin joint, but I've talked about this a few times. We model things. We don't get exact models. We model them to get approximations that we can design on. So that's one way you can model the cutoff wall on a dam, is like that. All right. So what you're going to end up with then is these distributed loads, and what we want to figure out is what's going on with this soil load here. What's the force per unit length along at the end of that is kind of what I'm looking at. All right. Now this is going to involve getting the resultant forces from these distributed loads. So your soil force will be like that, and that will act through the centroid. Now you don't know what the magnitude is of it yet. You'll be able to find that, but you do want to lock in its location. And I believe that's 0.88 meters, if memory serves, which is 2/3 of 1.32. Now what's going on here is when I look at that, I know that, I always start with a free body diagram, which is just, I think a lot of engineers start their morning by drawing a free body diagram of their day or something. It's just kind of very ingrained. I actually had a friend in college who constructed a Venn diagram to prove that his girlfriend couldn't see someone else and him at the same time. And I came in the living room and he was crunched over in a little rocking chair trying to prove this to himself and having all these problems. He was obviously needed some assistance. So I tried to help him work through that a little bit. He was having some problems. He was seeing someone else at the time too, so I don't know. I chose not to point that out to him. Yeah, exactly. It was very complicated. He was lost in the details. So he was having problems. Yeah. We got through it somehow. Okay, so what we do next is I'm looking at that, and I'm going to go sum of MB. I know I'm going to do that because I've got a pin joint. The last unknown, because all I can do with statics, is F soil, okay? So I know I'm going to take a moment about B to get that done. Now, if I'm going to do that, then what I want to do is dimension everything from the pin joint, okay? So we're solving the problem, but I'm also trying to talk a little bit about the process. This is the thinking that goes into solving the problem. Moment about B, so I want to dimension from B. That's what I want to do. So I'm going to want this dimension here. Now notice, why was that 2/3 on that dimension? Why not 1/3? Yeah, and I'm coming from the vertex, right? Not from the right angle, but I'm coming from the acute angle. The centroid of a triangle is right there. It's base over 3 from the right angle, which leaves 2/3 of the base from the acute vertex there, okay? That's why I'm using 2/3. Good? Okay. And then I've got the distance up from the right angle, so this will be 1/3, won't it? So that'll be 0.8 meters coming up because I'm doing 2.4 over 3. All right. And I think you should be able to come up with that load there. The load will be on account of that force of the water, basically. Okay, so that's 2.4 meters over 3. That's the 0.8. So what I'm going to end up with then is a force right here. So that's F water. Okay. Now I also have the weight of the dam, the wall of the dam right there, and that is 17,000 newtons. And I have the weight of the floor right there, and that is 9,500 newtons. Okay. So I'm going to need a moment arm for that too. All right. Now, what I'm doing is I'm breaking everything down. I'm putting all the forces, and I want all the dimensions on that sketch. And again, I keep going over this, but I'm just not that smart. I'm not smart enough to calculate all that stuff at once and put it into one equation. If I do that, I'm going to make a mistake. At some point, I just am. All right. And when I've worked, I've had a contractor jump off a grader, and I'm surveying, and he's in my face saying, "That grade stake's wrong, man." And that leads to a rather direct conversation sometimes. Okay, and it's fine. You want it to have the habits so that you don't bust the numbers. It matters when you work. Okay. And I got that one right. He was wrong, so that was fun. And he was actually quite polite about it, but he wasn't. He was very direct. It matters. He's burning time pushing dirt around. It's got to be right. Okay. So that's the deal. So all right. So there we go. So now we're just going to do that sum of moments about B equation, and what we're going to come up with here is the force of the soil pushing up on that. And I've got everything just all set up and sketched and ready to go. So now I just plug it into the equation. So, you're going to find the force of the water. That's just the area of that triangle. And you're going to multiply that by 0.8 meters. And then you're going to look at it and you go, well, if that force of the water, that's coming around like that, and that's clockwise, and that means that's negative. That's how I approach that, okay? I'm not going to worry about that 17,000 because it pushes right down at B. I'm going to have minus, 9,500 newtons times that moment arm. And then I'm going to have the force of the soil up, and that's my unknown. And that'll be times, 0.88 meters? Like so. Did I get everything that I need? I think I did. All right, and then I'm going to find the force of the soil. All right. And I believe that's 9743, if I'm not mistaken. Okay. And then see what the F of the force of the soil is the area of that triangular diagram, like that. What I really want out of this problem is I want to know what this value is right there. And what that's going to be is 1/2 times whatever that value is, and for whatever reason I called it PC, I don't know why, but I did, times the base, and the base is 1.32 meters, and that equals the 9743. So that'll get me that soil load per unit length, okay? And that's going to be 14,762 newtons, okay? And that's per meter, I'm sorry, there we go. So that's that value at C in newtons per meter. Now, if you're doing this, and this is actually a project, what you're going to do, you're going to get that into a pressure. You're going to look at the width of the dam and divide that out and get that into a pressure. And then you're going to check your soil and see if it can handle that much force, that pressure pushing down on it without essentially collapsing and kind of caving in. And then you'll look at that number to make sure the soil can handle it. And then to finish this thing, so we good with that? So I guess, we got any questions on this? What's going on here? The moment about B? Okay. But, especially a problem like this, I'm not going to just try and do all the area calculations for the forces and the centroid calculations all at once and throw it into one big equation. That's just, that isn't how I would approach it. Okay. I want a cleaner diagram first. So we good? Okay, sum of fx equals 0. To finish this thing up, you'll get rbx from that, and that is 2880. And then sum of fy equals 0. And you'll do that, and that will get you rby. Okay, and that'll get you RBY, and RBY is 16,757 newtons. There we go. So we good on that one? Okay. Okay. Last one is this. All right, this is a pump in a wet well. Okay, wet wells are kind of unpleasant places to actually work in, so they often put a little rail there down the edge of the wet well. You put a chain on the pump and you can just kind of pull it right out. It kind of levers into a flange fitting with the pipe there on the wall. That's usually how that works. So we're going to pull this thing up and out. All right, we've got roller A rides on the track. The track runs on that vertical wall. Assume B is smooth. The cable is used to lower the pump. Okay, we want to find the force in the cable and the reactions at A and at B. And then, so we want to do that. Now, of course, we got to get a free body diagram is what we need. Now, we've got smooth connections and a roller at A and a kind of half circle kind of thing there at B. So how are those reactions going to look at A? In what direction will the reaction at A go? We got a vertical wall and a smooth connection and a roller. Which way is it going to go? Yeah, something like that. You good with that? Okay, RA. Semicircular projection there from the pump and a horizontal floor there at B. So which way will that reaction go? And a vertical, okay. 3 reactions. Okay. All right, now, I've given you an awful lot of problems with pin joints, but you notice this one doesn't have a pin joint, does it? Darn it. Okay, so we got to solve for one unknown. Okay, we got 3. We got to solve for 1. So what is the strategy to do that, do you suppose? If I want to come up with one equation and solve for one of those unknowns. Yeah. Yeah, I think C would work. I think there's a couple points you could take moments about. That would work. Now, why will that work? Why is that a good idea? Because I've got that force in the tension, and if I just project A out, that goes right through that point, doesn't it? So by taking a moment about C, you will eliminate A and C from the equation. You can solve RB. Is that good? So sometimes you have to think a little bit and project forces to find intersections. You could also, if you wanted to, figure out where that point is. Take a moment about that. You could solve for the tension in C also. Either way, okay? So sum of MC, that will get you RB. 353 for that, I think. And then sum of FX and sum of FY should finish it up. Let's see, you probably want to do a sum of FY first, though, I think. Like that, okay? So we got any questions on that? Doing all right? Okay.